Yeah, we've been talking chapter 9, not 19, chapter 9, and we've talked about stoichiometry. And I think last time we got into really basic sort of stoichiometry problems. And what makes something sort of a basic stoichiometry problem is you're really just given one piece of information about somebody in a chemical reaction, and you want to really find some information about somebody else that's in that chemical reaction. And really, that's the whole purpose of stoichiometry. It's really, as we talked about, sort of just a conversion factor. And there's really four basic steps. You want to always make sure that you have a balanced equation. Remember that if the equation is not balanced, then none of the calculation is going to work correctly. You then want to pretty much take whatever they give you and convert it to moles. So whatever unit it may be in, you pretty much want to get it to grams, and from grams you want to get it to moles. That again is the molar mass from the periodic table that allows you to do that conversion. Once you do that, you have yourself set up to do the mole-to-mole relationship from the equation. And when we look at an equation, the mole-to-mole relationship can be found by looking up the coefficients. And this is really the whole purpose of stoichiometry. 3, I guess, comes after 2, is to use a conversion factor. So, for example, if we had information about A, but ultimately wanted to get over to C, we could go 2 moles of A is equal to 2 moles of C. And again, those are just the coefficients from the balanced equation, which is why it's really important to make sure the equation is balanced. That will give you really 2 conversion factors that you could use in a particular problem. You will only use one depending on what your problem is asking for. But that's basically what stoichiometry is. Again, just a conversion factor. And basically where we get that conversion factor is from the balanced equation, rather than say look it up in a table. Last step is usually if you are in moles, which you should be at this point, you oftentimes will want to maybe convert to some other unit. On the back end, very common, moles to grams is a very common sort of conversion there. And once again, that would be like above there, the molar mass would be what you would use for that. Any questions on any of that stuff we talked about last time? So I think we did a problem. So I think where we left off was this problem, I think. So why don't you give it a go here, follow those steps. How many grams of cisplatin, whose molar mass is 300.1 grams per mole, can be obtained if you started with 0.7752 grams of K2PtCl4? So take a few minutes there to see what you come up with. This is really a basic stoichiometry problem. We're given really one piece of information about somebody in the equation. We ultimately want to get over here to that guy in the equation. And that means we're going to follow our 4 steps. The first thing, again, is to balance the equation, which it already is, so that's good. The second thing that we need to do is convert whatever they give us into moles. And in this case, we do need to do that since we were given this guy in grams. They were nice enough to give us the molar mass here. So if they didn't give you the molar mass, you would need to go to the periodic table and add up everything. And in this case, it looks like 415.1 grams per mole. Grams are going to cancel. Again, you don't necessarily have to get an answer at this point. You could continue on with the calculation, but if you did get an answer, once again, I would not round too much until the end. That's going to get you 0.001867 moles of our K2PtCl4. The next step is the mole-to-mole relationship. And once again, we're going to look at the 2 things we're interested in. One thing you're interested in is what they gave you. The other thing you're interested in is pretty much what you're trying to find. And from the equation, we can see that the relationship is pretty much a 1-to-1 relationship. So for every 1 mole of K2PtCl4, you get 1 mole of our product here, our PTNH3, I guess. I think it should be 2, but we'll go 3. Cl2. So we're going to use that as our mole-to-mole relationship. This is really the stoichiometry part of the calculation. Again, since I did get an answer, I'll just continue with my number there. Again, opposites canceling, so we'll go with 1 mole of this guy on the bottom here. and 1 mole of our product up on top. I think I could do that math there. So 1-to-1. So 0.001865 moles of, I see that wrong thing. PTNH3 2Cl2. At that point, we do need to do step number 4 since we are looking for grams. So here you should always be in moles. And in this case, we're going to go to grams. And again, they were nice enough to give us the molar mass. Otherwise, you would need to look it up again on the periodic table and calculate it yourself. So we take our number there. We're going to use the molar mass of our product. And that one is 300.1 grams per mole. Moles on the bottom so that they cancel. Going to multiply basically by 300 there. 0.1. Going to get us 0.5604 grams of our product in this case. This is a product, which means it is a yield, and this would be known as the theoretical yield in this case. Yeah. Questions on that there? So basic stoichiometry problems are pretty much these 4 steps. You always just go in order. If something's done for you, go forward, never backwards. And once again, they would actually prefer you here at the school just to do it all in one calculation, which obviously would just roll from there to there to there, basically, without giving numbers in between. Any questions on those steps there? All right, so now we talked about sort of basic stoichiometry problems. We're going to talk about a little bit more complicated sort of stoichiometry problems and sort of what we need to do in those. And those are sometimes referred to as limiting reagents. And the idea of limiting reagents, they're also sometimes referred to as limiting reactants, is the idea that when you do a reaction, one of your reactants will essentially get used up first before the other one. So there's always going to be one that's going to get used up first. And why that's really important is it's going to be important for how much product you can form. So if you take just a basic example, if you have A plus B to make A and B, let's say this guy is my limiting reagent. As soon as I run out of A, there is no chance that I can make any more product because obviously here I need A and B to come together. And if I have no more A, I'm not going to be able to make any more product. So it is the limiting reagent that always determines how much product you can make. So that's why the limiting reagent is really important. By the way, the other reagent is typically what is referred to as the excess reagent. So you have a limiting reagent, which is one that gets used up first. When the reaction's over, you pretty much have none of it left over. It's pretty much zeroed out. You have an excess reagent, which you have plenty of. And when the reaction's over, you actually have some of that left over. So you have some of that excess reagent sort of left over when the reaction is done. So if you think about the story of the experiment we did the other day with the yellow, the Ki was the solid that you weighed out was the limiting reagent, and the liquid part that you have plenty of was the excess reagent, and that's why you did your calculation based off of how much solid that you weighed out. So if we look at these reaction buddies here, we need a guy and a girl here to make a pair. Obviously, we could see if we use 1 and 1, 2 and 2, 3 and 3, we are now out of guys, and that would mean that our guys would be our limiting reagent in this example. The girls here would be our excess reagent. Also very common, these type of problems is they ask you something like how much excess reagent you would have left over. So in this case, we would have 2 left over, and those are sort of calculations that you can sort of figure out. It's kind of like hot dogs and hot dog buns. They give you 8 hot dogs, I think, or no, 8 buns and 10 hot dogs, and never have enough to fully complete it in a package. So if we look at this reaction here, and let's just say that we are starting with 4 moles of S. We're going to start with 4 moles of S. And we're going to start with 20 moles here of the F2. So how do you know it is a sort of limiting reagent problem versus just a basic stoichiometry problem? Well, the way that you know that you need to sort of do this limiting reagent sort of step, if you will, is you can get to moles of each reactant. So if you have both reactants and you have information given to you that you can easily convert that into moles of each of the reactants, then you know it's a limiting reagent problem. You have to figure out which one's the limiting reagent. Now, like the examples we did previously, we pretty much were only given one piece of information, maybe about one reactant, one product. We weren't given everything about both reactants. So that is how you know that you have to do the step. There are actually multiple ways that you could do these type of calculations. So we'll do one way, and I'll explain maybe another version that's very popular as to how you can do that sort of calculation. Now, the way we're going to sort of do it is pretty much the way that we did basic stoichiometry problems. So we're going to follow the same 4 steps. You're going to still balance the equation. You're going to convert to moles. Pretty much no matter what method you use, they pretty much both start that way. Right around here, we're going to pause and we're going to figure out the limiting reagent. So we're going to figure out the limiting reagent. Once we figure out the limiting reagent, because it is the one that determines how much product you make, we will pick back up with our steps here with the limiting reagent and do our mole to mole relationship. And then do, obviously, here our moles to some other unit. All right, so in this particular case, we obviously have an equation. It's balanced. Bless you. We have the moles of each reactant, which tells us it is definitely a limiting reagent problem. So we actually have step 1 and step 2 kind of done for us already because they're already in moles and we don't have to worry about it. So now we're at the point where we want to figure out which one is the limiting reagent. So in this method, the way you can figure out if something is the limiting reagent is you're just going to do a really simple sort of calculation to figure out, for example, if I wanted to use up all my sulfur, I want to know how much fluorine is needed. So this is sort of the calculation I'm going to do. Remember that starting amounts here of these guys is we have 4 moles of sulfur and we have 20 moles of the F2. So that's kind of like our starting amount. So to do this calculation, we're going to take our starting amount of sulfur, which I want to use up. I'm going to go to the equation and find the mole to mole relationship between these two. And that is a 1 mole to 3 mole relationship. So we're just going to do a little calculation here where I go 1 mole of sulfur from the equation gives me 3 moles of F2. The moles of sulfur will cancel. That's going to give me 12 moles of F2 is needed. First off, any question on that calculation? So just a simple calculation between the 2 reactants to figure out if you want to use up all one of them, how much of the other one do you need? Now, what do I do with that information? Well, I just calculated that I needed 12 moles of the fluorine. I want to then compare to my starting amounts. And I'm starting with 20 moles of fluorine, and I only need 12. Do I have enough? I do have enough, yeah? And because I have enough, what that means is this guy's going to be the excess reagent. And by default, this guy will be the limiting reagent. So the good news is you just need to figure out one of them, which one's the excess or which one's the limiting, and the opposite thing is happening to the other. Now, just to show you, if you wanted to, you could choose either reactant. It doesn't matter which one that you choose. So if I wanted to do, say, the opposite calculation, let's just say, for example, I wanted to use up all my fluorine. How much sulfur is needed? So again, you could choose either reactant to kind of do this calculation. And if I did that, I would start with my fluorine, which is 20 moles. I would use my same relationship from the equation, just opposite. 3 moles of fluorine is 1 mole of sulfur. The moles of fluorine will cancel. I will take 20 divided by 3 is 6.67 moles of sulfur is needed. If I did this calculation, I would then compare it to how much sulfur I'm starting with, and I'm starting with 4, and I need 6.6. I do not have enough in this case, right? So I do not have enough, which would tell us exactly what we figured out from the previous calculation, that that guy's the limiting and that guy's the excess. You do not have to do both of the calculations. You could choose either one, and they both will tell you the same thing. They both will tell you which one's the limiting reagent and which one's the excess reagent. Any questions on that there? So now that I know, for example, which one is my limiting reagent, which is the sulfur, I now am going to pick up with step number 3, and I want to make sure that I use the limiting reagent in that step. I also want to make sure that I use the starting amount of the limiting reagent. So if we were going to go to step 3 here, I would do my 4 moles of sulfur. I would then do the mole-to-mole relationship between sulfur and my product here. And that would be 1 mole of sulfur is 1 mole of SF6. That gives me 4 moles of SF6. I then could use the molar mass of SF6 that I could get from the periodic table. That's 19 times 6 for the fluorines plus a 3207 for the sulfurs. That would give me 146.1 grams per mole. And that would tell me in this case, I should get about 584 grams of SF6 produced. This again would be my theoretical yield in this case. And this would obviously be our 4th step. So in this method of doing limiting reagent problems, we pretty much do the exact same things we do for a basic problem, except halfway through there, you got to stop and do a calculation to figure out which one is the limiting reagent. Once you do that, you continue on with the starting amount of your limiting reagent to figure out how much product you produce. Questions on that there? Once again, to determine which one is the limiting reagent, that has to be done by some type of calculation. It cannot just be like the smallest number, which is very common what people think. There's like the smallest one or the smallest number of moles, and then that's going to be your limiting reagent. So you have to do some type of calculation to determine which one's the limiting reagent. It will not always be like the smallest number of moles or something like that. So you have to actually do a calculation. Now, this is one method, probably a more common method of doing these problems this day and age is you actually just do 2 separate calculations. So for example, here I would start with the sulfur and do a stoichiometry calculation to the product and figure out how many grams of product it would produce. I would then do a separate calculation with the fluorine starting amount and figure out how much product it would produce. Whichever one produces the smaller amount of product is both the limiting reagent and your theoretical yield. So that's like the very common sort of approach these days, is just to do 2 separate calculations, one of which you won't even need at all. You throw it away basically, and whichever one gives you the smallest amount of product produced is both, again, your limiting reagent and your theoretical yield. So if you like that method better, you could do that as well. Any questions on that? Okay, so let's take a look here at 1, I think. I'll scroll this through. All right, so why don't you try this? We are looking for, if we take 6.83 grams of iron, we react it with 9.34 grams of sulfur. Which one's the limiting reagent and how much iron's 2 sulfide is going to be produced? Iron is 5585. Sulfur is off. I know this is a limiting reagent problem because of the information given to me. I have grams of this reactant. I have grams of that reactant, which means I could definitely get to moles of each of those. And that's really your key to know that this is a limiting reagent problem, which means that you do need to, at some point, figure out which one is the limiting reagent. So first couple of steps are basically the same. We're going to have a balanced equation, which we do, so that's good. We're going to convert what they gave us into moles. So for my iron here, we're going to go 6.83 grams. We're going to use the molar mass from the periodic table, divide by it 5585 grams per mole. That will get me there 6.83 divided by 5585, about 0.122, we'll call it 3 moles of iron. I'm going to also do the same thing here for my other reactant, which is sulfur. So I got 9.34 grams of sulfur using the molar mass from the periodic table, 3207 grams per mole. Will give me here 9.34 divided by 3207, 0.2912 moles of sulfur. Any questions so far? So these represent really the starting amounts, right, of each of these guys. So that's how much I have to start with, basically, of each of these. Because it is a limiting reagent problem, I do need to do that calculation. So in this case, to figure out my limiting reagent, I'm going to figure out how much sulfur is needed to use up all the iron. So again, I'm just going to do a basic little calculation between the two reactants. So I'm going to take my moles of iron, 0.1223 moles of iron. I'm going to do the mole-to-mole relationship between these two guys, which is a 1-to-1 relationship based off of the coefficients. So 1 mole of iron on the bottom gives me 1 mole of sulfur up on top. The moles of iron will cancel, and that will give me 0.1223 moles of sulfur is actually needed. Any question on that calculation there? Now I'm going to compare the moles of sulfur needed to the moles of sulfur I'm starting with. And when I compare here, do I have enough sulfur in this case? I am starting with 0.29 moles and I need 0.12 moles, so I do have enough. So again, because I have enough, what that tells me is the sulfur is my excess reagent. By default, the iron here would be my limiting. Again, I don't really need to do the other calculation to verify unless you wanted to, but that will tell you basically both. Any questions on how we determine that there? Now that we determined that, we're going to go with the starting amount of iron, which is our limiting reagent, and actually figure out how much product we produce. So continuing on here, 0.1223 moles of iron, which is our limiting reagent. We're going to now do the mole-to-mole relationship between iron and the product, which also is a 1-to-1 relationship. 1 mole of iron gives me 1 mole of my product here. The moles will cancel. If I got an answer at this point, I would be in moles of my product, but I'm actually looking for grams. So I'm just going to do the molar mass calculation here without getting an answer. That's basically just adding these two together, I think. So we're just going to add those guys together there, 5585 plus a 3207, going to give me 87.92 grams per mole. So we'll use that. Again, opposites cancel, so the grams are going to go up on top here. And the moles here will go on the bottom so that they cancel. And that will give me 0.1223 times 87.92. And divided by nothing, I think. So about 10.8 grams of my FES would be produced. This again would be our theoretical yield. Any questions on those steps there? Now, again, I mentioned the other very common approach that people are taught these days. So since we have it here, I'll just kind of show you what I meant by that. If you're going to kind of take the other very common approach is you would just start with your iron, for example, and you would take your 6.83 grams of iron. You would convert it to moles using the molar mass, 5585 grams per mole of iron. You then would do the mole-to-mole relationship between iron and the product, which is a 1 mole of iron to 1 mole of our product. And then you would use the molar mass of our product, which is our 8792 grams per mole. Again, here the grams would cancel, the moles would cancel, the moles of this guy will cancel, and you would end up with 6.83 times our 87.92 divided by 5585. You're going to get our 10.8 grams of our product. You then would do a calculation with sulfur, starting with the grams of sulfur, 9.34 grams of sulfur. You would convert it to moles, 3207 grams per mole of sulfur. You would do the mole-to-mole relationship between sulfur and the product, which also is a 1-to-1 in this case. And you would use the molar mass here, 8792 grams per mole. And that would get you 9.34 times 8792 divided by 3207 would get you 25.6 grams of our product. So this is what I was talking about. You would do two separate calculations, starting with the starting amount of each reactant. Yeah. Right, we haven't done that part yet. You could do any of these and figure out how much is left over. We'll talk about that in just a second. So if you did this, what you would do at the end is compare these two numbers, and the smallest number that you get, a product, would be your theoretical yield and your limiting reagent. You then wouldn't do nothing with that calculation. So you kind of do a calculation you wouldn't use basically all the way through. So it's your choice if you wanted to do it that way or the other way. Those are, again, two very common ways to do that. Now, to answer your question, we can also figure out, in this case, how much excess reagents left over at the end of the reaction. And we could actually do that based on our calculation up here. So we know from our kind of limiting reagent calculation that we needed this much of the excess reagent. We know we have this many moles of the excess reagent. So if we wanted to figure out how much of the excess is left over, we basically just subtract those numbers. We take the moles of the excess reagent we started with. We minus it from our calculation here of how much we needed of the excess reagent. And that would get us 0.2912 minus 0.1223. We have 0.1689 moles of sulfur left over. And we can multiply that by 3207 grams per mole, which is our molar mass of sulfur. And that will tell us that we have about, I'll go up here, we have about 5.42 grams of sulfur left over at the end of the reaction. We started with 9.34 grams, right? And we got about 5 grams or so left over. So we use about 3 and change of the sulfur in this reaction. Now, if we chose the other reactant to do this calculation for, we would need to go back and basically do this calculation to figure out how much moles of the excess reagent were needed if we were going to answer this question. You definitely would have to go back if you did the bottom approach and go back and do that calculation anyways. So sometimes doing that calculation, the first approach, will actually help you if you were asked that question. And it does depend on which one you kind of choose to do it. Other questions on that there? All right, let's try a couple more here, just make sure. And I'll scroll this across streams, pretty much what we just did. All right, so I want to try this one here. We're going to go with 622.7 grams of NH3 reacts with 1,241 grams of CO2. Which one's limiting reagent and how much product would we produce in this case? They were nice enough to give us the molar mass of everything, so you don't have to calculate. All right, see what you come up with here. We could also get the moles of this reactant. That, again, is your key to know this is a limiting reagent problem. I'll be honest with you, most problems won't even ask you that. They just assume that you'll know that It's a limiting reagent type problem. So they definitely will not in like blinking lights tell you, hey, this is a limiting reagent problem. In most cases, you have to be able to kind of determine that based on the information given to you. So with that being said, we do want to really just take our same approach here. I'll just get rid of that big line I just put in the middle of the page there. All right. So we got our balanced equation. So that step is done. Again, regardless of which approach, we're going to convert everybody into moles. So for the NH3 here, we're going to take our 6, it was 22, I think, right? 0.7 grams. We're going to use the molar mass of NH3, which is our 1703 grams per mole. And that is going to get us there 622.7 divided by 1703. We're going to end up with 36.565 moles of NH3. We'll do a similar calculation here for the CO2. We got 1,241 grams of it. We will use the molar mass there. Again, if it was not provided for you, you would need to go to the periodic table and calculate it yourself, which is also very common. What you have to do in these type of problems, they're usually not given to you. Would give you 28.198 moles of CO2. Remember, again, this is basically your starting amount. So again here, I'm just going to pick whichever reagent I want, and I'm going to figure out how much of the other one I need to use it up. So in this case, I'm going to figure out how much, I will go with CO2 is needed. So this is really my limiting reagent sort of calculation to figure that out. And if I do that, I'm going to take the moles of my NH3. And I'm going to do the mole-to-mole relationship between NH3 and the other reactant. And from the equation, I can see that for every 2 moles of NH3, which needs to go on the bottom so it cancels, I will also need to put in there 1 mole of CO2. And again, that comes from the coefficients here in the balanced equation. So that is going to tell me in this case here, 36.565 divided by 2, about 18.283 moles of CO2 is needed in this case. Once again, we're going to compare how many moles of CO2 is needed to our starting amount of CO2. And in this case, actually, looks like we're okay. We have 28 moles of CO2 to start with. I only actually need 18 moles of CO2. So we do have enough. And because we do have enough, that again means in this case, our CO2 is our excess reagent. The NH3 is our limiting reagent. Any questions on how to determine that there? Okay, so once we have determined our limiting reagent, we want to use it to figure out how much product we're going to produce. Again, we do want to roll back to the starting amount here of our limiting reagent. So we'll take our 36.565 moles of NH3. Now we're going to do a mole-to-mole relationship between NH3 and our product, which in this case is a 2-to-1 relationship. So 2 moles of NH3, and this is the big stoichiometry move here, 1 mole of our product. Moles of NH3 will cancel. Again, at this point, I actually want grams, so I'm not going to get an answer. I'm going to kind of just continue on with the calculation. I would, at this point, if I stopped, have moles of our product, which if you wanted moles, obviously you would get an answer at this point. But we would use the molar mass, which again was provided for us, and if not, you would need to look it up on the periodic table. Moles are going to go on the bottom here, so they cancel. 6006 is going to go up on top, so that we end up with grams. And now if we take our 36.565 times 6006 and divide it by 2, we're going to end up with 1098 grams of our product here. At this point, we can clean it up. And actually, in this case, it looks like that should be good. Everybody's 4, basically significant figures. So that will be good. This would be, once again, our theoretical yield in this case. Any questions on that there? So again, with this approach, it's really still the same 4 steps, just that little mid step there. You have to do just a really small calculation, and you can figure out which one's the limiting reagent. Again, if you want to do the other approach, 2 separate calculations, whichever one produces the smaller amount of product is your theoretical yield and your limiting reagent. Any questions on those steps there? Okay. So speaking of yields, let's actually talk officially here about the different types of yields. Scroll that through. And obviously here we could also figure out how much of the excess reagents left over by subtracting, and that'll give us our moles, and our molar mass there would give us 437 grams of that CO2 would be left over. All right. So when we talk about yields, there's 3 types of yields that we have in a reaction, basically, that we look at. And that is the theoretical yield. The theoretical yield that we've been talking about is your maximum amount of yield. A yield does have to be a product, so that's what yield means, basically. That's what the arrow means, to yield. So that's what's on the product side, past the arrow. And a theoretical yield is basically using the equation and doing a stoichiometry problem and your starting amount based on the equation and what you're starting with in terms of reactants, how much product you should make if everything went perfect. There's no side reactions, didn't spill anything, didn't lose anything along the way. That is, again, the max amount of product that you should produce if everything went perfect. We know that things do not go perfect. So that brings us to the actual yield. And much like the name implies, the actual yield is actually how much you got when you did the reaction. And you can put both of those together to calculate what is very commonly calculated in stoichiometry problems, which is known as the percent yield. And the percent yield is the actual yield divided by the theoretical yield times 100%. In most book type problems, the actual yield is usually given to you. So somewhere in there it tells you, hey, you produce this much of the product. So the actual is usually given to you in book problems. This one, usually you got to calculate, and it can either be a basic stoichiometry problem, it could be a limiting reagent type problem, but some type of calculation that you need to do. In real life, obviously, like you did in that experiment, you would figure out how much you produce, like if you're yellow on your filter paper that you did in that particular experiment. Usually we want a high percent yield, but not over 100%, because that usually is not a good thing. It usually means a lot of times some type of mistake perhaps happened in that case. But, you know, high 90s, mid 90s, there's really, really good yield. We do not want a low percent yield. That means you definitely probably screwed up somewhere along the way as well. You lost a lot of stuff. All right, so let's try one here. Actually, yeah. All right. So let's say we had 2.46 times 10 to the 4 kilograms of TiCl4. Molar mass is 189.7, reacts with 1.44 times 10 to the 4 kilograms of magnesium. Molar mass there, 2431. Calculate the theoretical yield of Ti in kilograms and calculate the percent yield there. Actually, let's skip this one for a second. Let's do this one, actually. I think I like this one better. We'll come back to this one here, I think. Let's actually do this one here. All right, let's do 100 grams of ammonia is reacted with 100 grams of carbon dioxide, and 120 grams of this product is produced. What is the percent yield? So let's do this guy here. Nitrogen is 1401. Carbon 12.01, and percent yields, which again is our actual divided by our theoretical times 100%. In this case, they told us that we produced 120 grams of our product. That would be the actual, so we have that obviously. Now, the theoretical, as we talked about, does come from a calculation, so we will need to do a stoichiometry calculation to figure out how many grams of our product we're going to produce here. We also hopefully should recognize that I have grams of the first reactant and I have grams of the second reactant, which means I definitely could get the moles of each of those. So this is not a basic stoichiometry problem. This is a limiting reagent type problem that we have to do because we could get the moles of each of those things. So we're going to have a balanced equation, which we already do. We're going to get our moles of each of our reactants to start with. So NH3 here, we're going to take 100 grams of NH3. We'll use the molar mass, which I think we might have calculated in a previous problem. And that is 1703 grams per mole. If you go to the periodic table, 1 nitrogen at 14 and 3 hydrogens at basically 3 will give us a starting amount for our NH3 of approximately 5.872 moles of NH3. We're going to do a similar calculation for our other guy, which is CO2. We're going to start with 100 grams of CO2. Going to the periodic table, 1 carbon at 12.01 and 32 for the 2 oxygens gives you 4401 as the molar mass of CO2. That is going to get us here a starting amount, if I don't do 1,000, let's see here, 4401 of 2.272 moles of CO2. Again, this is basically our starting amount of each of these guys. Any questions up to there? So because it is a limiting reagent problem, we have to do our little calculation. So in this case, I'm going to figure out how much CO2 is needed to use up all the NH3. So I'm just going to do that little calculation. So I'll take my NH3, 5.872 moles of NH3. I need to go to the equation, find the mole-to-mole relationship between those two. And from the equation, it's 2 moles of NH3 to 1 mole of CO2. So 2 moles of NH3 to 1 mole CO2. That's going to tell me here 5.872 divided by 2, about 2.936 moles of CO2 is needed. Again, here I'm going to compare to my starting amount of CO2. And in this particular case, I do not have enough, right? I have 2.2 to start with. I need 2.9, so I do not have enough. And that's going to mean that in this reaction here, it is the CO2 is the limiting reagent, and by default, the NH3 would be the excess. Any questions on that? All right, now that we know it's actually the CO2 here is our limiting reagent, we're going to use that to figure out how much product, which would be our theoretical yield. So we'll go 2.272 moles of CO2. I now want to do the mole-to-mole relationship between my CO2 and the product in this case. And that is going to be CO2, which is 1 to 1 in this case. So that's not too bad. So 1 mole of CO2 on the bottom to 1 mole of my product up on top. Moles of CO2 will cancel. Once again here, since my actual yield is in grams, I do want to actually use grams here for my theoretical yield. So I'm not going to get an answer. I'm going to go back to the periodic table and calculate the molar mass of my product. So that is 2 times 1401 for the nitrogens, plus 4 times 1.008 for the hydrogens, plus 12.01 for the carbon, and 16 for the oxygen, which I think we also had in the previous problem, 6006 grams per mole from the periodic table. Those will cancel. It gives me 2.272 times 6006, basically about 136.5 grams of my product here. And this would be my theoretical yield. Any questions on that there? Now that I have my actual and now that I have my theoretical, I could figure out the percent yield. And that is going to be my actual, which was 120 grams, divided by my theoretical 136.5 grams, times it by 100% in this case. Going to get me 120 divided by 136.5, times it by 100, a little 87.91%. Not terrible. in that case. Any questions on that? Now, when you calculate percent yield, most commonly, you'll probably do grams and grams, but it doesn't have to be. It could be moles and moles. As long as the two units are the same on top and bottom, you could calculate percent yield, again, as long as they're the same unit. Any questions on percent yield, limiting reagents, stoichiometry? All right, we'll lay it up there for today.